If you've been tracking AI research, you've noticed a massive architectural shift. Image generators are replacing UNets with transformers. But why, and what does that actually change under the hood? Traditional diffusion models use UNets to predict noise at each denoising step. UNets rely on convolutions and skip connections to preserve spatial resolution, but convolutions have a fixed receptive field. They struggle with long-range dependencies. In practice, that means the model has a hard time coordinating details across the entire image. Diffusion Transformers, or DIT, solve this by tokenizing the latent representation and feeding it into a standard transformer encoder. Every spatial patch attends to every other patch via self-attention. The math is straightforward. Self-attention captures global context in a single forward pass. With modern optimizations like Flash Attention, we reduce the memory bottleneck of quadratic scaling, making it feasible to train on massive datasets without blowing up VRAM. More importantly, DIT scales differently. When you increase parameters and compute, performance doesn't plateau like it does with UNets. It follows clean power law scaling. Text conditioning is handled natively through cross-attention layers, removing the need for separate clip encoders or complex conditioning blocks. The architecture is also resolution-agnostic, meaning you can train on latent space and scale to higher resolutions without architectural rewrites. This proves transformers aren't just for language. They're becoming the universal backbone for generative models. If you want to dive into the actual paper, the scaling experiments, and the architectural breakdown, I've linked everything in the description. Stay curious and keep pushing the boundaries.